All right, we're starting. All right, cool. So we got a midterm in a week, so I'm going to send out an announcement. I'll try to get it out today. Midterm announcement, like what sections are going to be on it, how to study for it. Try to put together a study guide for y'all. All right. So, today we start chapter 5. Chapter 5 is on eigenvalues and eigenvectors. So who has heard of eigenvectors? Okay. Has anyone never heard of an eigenvector?
No, we've heard it.
Okay. So, this will be new to some of you. Maybe some of you have seen this before. What the heck are these things? Okay, so let's start off with an example. Consider the matrix. Let's let A be the matrix 2, 0, 0, 3. Okay. I think I've actually used this this matrix as this matrix as an example before. But just to sort of show you what it does. So, if I take a vector in the x direction, let's say u, and I apply a to it, it will stretch it to be twice as long as such. Here's the vector AU. It's twice as long as u. Now, similarly, if I take a vector in the y direction, let's say v, and I apply a to it, it's going to make v 3 times as long, but still in the y direction, in the vertical direction. So you could say like this, about 3 times, 2 times, okay, yeah. So you could say this matrix A, it stretches things horizontally by a factor of 2. It stretches things vertically by a factor of 3. So that's kind of easy to understand. But what if a matrix was a bit more complicated? So as a second example, now consider a different matrix, 5, -1, -1, 5. With this matrix, it's not so obvious what it does, okay? But you may still want to ask the question, does it stretch shapes in some particular direction?
Yes.
It does, in fact, and we're going to try to find what those directions are. They're sort of natural directions that are somehow inherent to that matrix, which is where the word eigen comes from. Eigen means, eigen is German for like proper or belonging to or natural. So we're going to be trying to find what are the natural orientations or directions or axes along which this matrix acts. In fact, I'll show you one. So let U equal 1, 1. And let V equal negative 1, 1. Then if we calculate the action of A on U, all right, so let's see, 5, negative 1, negative 1, 5 on 1, 1. What do we get? 5 minus 1 is 4. Negative 1 plus 5 is 4. That's 4 times U. And similarly, A on V is 5, negative 1, 5 on negative 1, 1. What do I get? I get negative 5 minus 1 is negative 6. And 1 plus 5 is 6. Hey, that's 6 times V. So in this example, the two natural directions for the matrix A were the 1, 1 direction and the negative 1, 1 direction. So let's give a name to these special directions. So if A is an n by n matrix, suppose that A times x is equal to lambda times x for some scalar lambda and some non-zero vector x. Okay, the non-zero part is important. And in this case, we call lambda the eigenvalue, and x is the eigenvector that corresponds to lambda. And by the way, in this class, usually I will abbreviate eigenvalue with E, G, V, L. And I'll also abbreviate eigenvector as EGVR. Yeah. Okay, so there's the definition of eigenvalue and eigenvector. So in the example, above, let's go back up to this example. Someone tell me, in this example A, what was an eigenvalue?
4 and 6.
4 and 6 were both eigenvalues. Someone in the back, what was the eigenvector corresponding to 4? One, 1 is correct, yes. So you can see I had an eigenvalue here and an eigenvalue here. And then I had an eigenvector here and an eigenvector here. Notice, though, even though, here, so let me just write it. So the eigenvalues were 4 and 6. The eigenvectors were 1, 1, negative 1, 1. So one thing that I can point out right now is any multiple of an eigenvector is still an eigenvector. Any non-zero multiple of an eigenvector is still an eigenvector. In fact, not only is it still an eigenvector, it still is an eigenvector corresponding to the same eigenvalue. So if you don't see why this is the case, check this for yourself. Okay, great, good. We got the definition. Now, in the example, in the example above on the screen here, I just gave you what the eigenvalues and eigenvectors were, but it would be great if we could find how to find them ourselves, especially because this is a super useful topic in this class. It's one of the more important things you're going to learn in this class. In fact, it's exactly what my 20D students are having trouble with right now. It would really be great if they showed up at this class. So the applications of eigenvalues and eigenvectors are numerous, way more than I can name, but differential equations, partial differential equations, image recognition, signals processing. Yeah, Upnam?
So if you multiply an eigenvector, the eigenvector value, are both those eigenvectors?
Sorry?
Are both of those eigenvectors?
Both what?
Where it says note that non-zero multiples of an eigen. Oh, okay, yes. So if you multiply an eigenvector by like some number, would the matrix that's changing it be like affected by that number or no?
Okay, here, I'll prove it. So here's what I was asking you to prove. So okay, here's a little proof of that fact. Suppose that V is an eigenvector with eigenvalue lambda, so A times V equals lambda times V, and that C is some non-zero number. Then what happens if you do A applied to CV? Well, the C comes out in front, and that's A applied to V, which, as we just said, is A times lambda V, which is the same as lambda times CV, i.e. CV is an eigenvector. So there's a little proof there that any multiple of an eigenvector is still an eigenvector corresponding to the same eigenvalue.
what is the geometric significance of eigenvalues and eigenvectors?
Well, good question. So that's what I was trying to show you with the two motivating examples here. We're trying to find the directions along which the matrix acts. In the first example, it took, say, like the unit square and stretched it out into twice as long in the x direction and 3 times as long in the y. In the second example, it would take like this little square, I suppose, and stretch it out. Okay, I mean, I don't know if I can draw this very well, but about 4 times in this direction, 6 times in this direction. I'm messing up my notes, oh man. So, that's the geometric meaning, and actually, really, I would love to have you watch some nice videos by 3 Blue 1 Brown, because he can animate them very, very nicely. So he's got good video on eigenvectors in his linear algebra series. I could try to draw it right now, but like he can animate it with a computer way better. So please watch that. So, how do we find them? Okay, how to find eigenvectors is you start by just writing down the eigenvector equation. Okay, so let's suppose that A times x is equal to lambda times x for some non-zero x and scalar lambda. Then I can rewrite that equation by moving all the terms to the left-hand side. And I can even factor out the x if I replace the lambda with a lambda times the identity. Oops. So what do we have here? I have a matrix. This matrix, A minus lambda I, is acting on a vector which is not 0, but we're getting 0. So this is equivalent to saying that x is in the null space of A minus lambda I. We have a special name for this space. So the null space of A minus lambda I is the eigenspace of A corresponding to eigenvalue lambda. And how do you, okay, so we learned when we studied the invertible matrix theorem, remember there's an equivalent condition to having a non-trivial null space. Maybe you remember one of our conditions from, well, I just kind of said the key word, a matrix is invertible if and only if its null space is trivial. Yeah, that was one of our invertible matrix theorem conditions. And so I'm saying right here is apparently this matrix, oops, sorry. Apparently, A minus lambda I is not invertible if it has an eigenvector. Okay, so let me write that as a condition. So x. Okay, so A has an eigenvector corresponding to eigenvalue lambda if and only if A minus lambda I is not invertible, which we have another criterion from the invertible matrix theorem that we just learned in chapter 3 that will be particularly useful for our purposes now, which is to say, remember a matrix is invertible if and only if its determinant is non-zero. I'm saying it's not invertible if and only if the determinant is 0. So that's the important condition I need, if and only if the determinant of A minus lambda I is 0. Okay, good. So that's an important equation. There's even a name for that. Okay, so if I define P of lambda as the determinant of A minus lambda I, then P is an nth degree polynomial in lambda, and it has a special name. It's called the characteristic polynomial. And lambda is an eigenvalue if and only if it's a root of the characteristic polynomial. Right? Because that's exactly what it means to say that the determinant of A minus lambda I is 0, which is exactly what it means to say you can find a non-trivial vector in that null space, which is exactly what it means to say that the definition of eigenvalue and eigenvector is satisfied. Okay. Cool. By the way, I notice a lot of you are just up and looking instead of taking notes. That's good. I'm glad to see that. One dude's drinking a beer. Holy crap, man. In class? Is apple juice? Oh, yeah, I've used that line too. That's a good one. Okay. Yeah, and for those of you that are taking notes, of course, hopefully you are aware that you can get the notes online too. So in case you missed something, it's all being shared with the cloud. Okay, so let me just define multiplicity. So if Lambda is a repeated root of P. We say it has algebraic multiplicity. All right, like if it's a twice repeated root, we say it has multiplicity 2. If it's a triple root, it has multiplicity 3, and so forth. So let's do an example. How about? How about if A is 7, 2, negative 4, 1. So first, let's find the eigenvalues and eigenvectors. Okay, so the determinant of A minus lambda I is the determinant of 7, 2, negative 4, 1 minus lambda 0, 0, lambda is the determinant of 7 minus lambda 2, negative 4, 1 minus lambda. Okay, so I get a 7 minus lambda, a 1 minus lambda, minus 2 times negative 4. What's this? I get a lambda squared minus lambda minus 7 lambda is minus 8 lambda plus 7 plus 8 lambda squared minus 8 lambda plus 15. Okay, so there's my characteristic polynomial. And luckily enough, I can factor it pretty easily as lambda minus 3 and lambda minus 5. So I get lambda equals 3 and 5 are my 2 eigenvalues. There's 2 of them, and they're 3 and 5. Okay, either one. Great, okay, good. How about, well, let's find the eigenvectors that correspond to those. So we have to handle them individually. Let's find the eigenvector. Let's first find it for lambda equals, how about 3? Okay, so I need to solve A minus 3I times x equals 0 for x, i.e. 7 minus 3, 2, negative 4, 1 minus 3x equals 0, i.e., okay, 4, 2, negative 4, negative 2, and let's just call x to be x1, x2. So if you row reduce, you get that 4x1 plus 2x2 equals 0. And then the second row is dependent on the first row, which is what we would expect.
confirm only square matrices have eigenvectors and eigenvalues, right?
Yes. So, all right, so we row reduce this system to end up with this equation. Right? That's all the information that the system is giving us. Well, what the heck, man? That's not enough to solve for x1 and x2. I thought that we're supposed to solve this problem. Oh, but remember what I was saying? You can always multiply an eigenvector by a constant, non-zero constant, to get another eigenvector. So there's a level of arbitrariness in this answer. There's actually an infinite number of correct answers, and the way you find it is just pick one. So just pick a value for one of these variables, a non-zero value, and see what the other one is. So the easiest one will be, I don't know, pick if, I want to pick the easiest one. So,
1.
actually, I'm gonna do better than that. If 2x, okay, all right, sure, yeah. Well, okay, yeah. Let's let x1 be 1. How about? So, x2 is -2. Okay. So 1, -2 is the eigenvector. And again, I say the eigenvector, although that's not totally right, since there are many correct ways to write it. Okay, let's see. Similarly, let's see. I'll just do how about for lambda equals 5, a minus 5i times x would be, what is it? 2, -4, -4, x1, x2, and this equals 0, 0, implies x1 plus x2 equals 0 after reducing. Okay, so which has the, again, you just make an easy choice. How about x1 equals 1? So x2 is -1, so the eigenvector is 1, -1. Cool. Okay. Any questions? Yeah.
Can eigenvector have independent? Can eigenvalue have independent eigenvectors?
Yeah. That's a trickier possibility that does in fact arise. Yeah. So we'll get to that. So here's another quick example. How about if A is, I don't know, how about 1, 2, 0, 3? Note that the determinant of A minus lambda I is the determinant of 1 minus lambda, 2, 0, 3 minus lambda is, as we know about determinants for triangular matrices, it's the product of the diagonal entries. So that makes it particularly easy to calculate eigenvalues when the matrix is diagonal. So anyway, I just wanted to use this to illustrate the following fact. Okay, that the eigenvalues of a triangular matrix are simply just whatever the diagonal entries are. And here's another fact. Or, in fact, here, sorry, let me write something first. So, since lambda is an eigenvalue if and only if the determinant of A minus lambda I is 0. So 0 is an eigenvalue if and only if, well, if lambda equals 0, I'm just left with the determinant of A equals 0, which we already know. In fact, I already mentioned it in this lecture. That only happens if A is not invertible. So that's the other fact I was going to write. A is invertible if and only if 0 is not an eigenvalue of A. Here's maybe the only non-trivial theorem of this section, which some of these proofs are kind of neat. I'm giving you guys practice with some of them on the homework. Here's one, which is not that hard to prove. The eigenvectors that correspond to distinct eigenvalues are always independent. Yeah, so eigenvectors corresponding to distinct eigenvalues, they're always independent. I have a proof of this fact. Man, I gotta decide whether to do the proof or not. I think I'll have a choice to either end the class with a little like Socratic quiz question or do the proof, but not both. Who wants to see the proof of this theorem? Who wants to do a quiz question? God damn it. I think I saw more hands for the proof, so I'm gonna try to do that one. Okay, so here's a proof of this. So we're going to prove it by contradiction, which is suppose that we have eigenvalues and eigenvectors. Let's say A v1 equals lambda 1 v1, A vk equals lambda k vk, where lambda 1 up to lambda k are distinct. None of these eigenvectors are the same. And v1 out to vk are non-zero. Suppose, for contradiction, that the set is not independent. So suppose that some group of them is dependent. And I'm going to arrive at a contradiction as follows by pick the first index. How about the smallest index p such that those first many vectors are dependent, okay? Right? Because they were given in an order, some order, it doesn't really matter, but just pick the smallest group, the first index, such that up to that, at that point, we get that v1 up to vp now is dependent. Right? If they're dependent, then for sure such an index exists. Maybe it's the same as k. Maybe it's the same as 1, but such an index exists. Okay. Sorry, it can't be 1 because the first vector is non-zero. Maybe it's 2. Maybe it's k. So now check this out. That means that vp is some linear combination of the vectors that came before it, v1 up to vp minus 1. Okay. Then let's take a on both sides of this equation. And I'll put an a right here, and that should be a on this one, right? Okay, that doesn't look so great to me. Rewrite that. All right, so a on v1 is equal to a on c1 v1 plus 2 plus cp minus 1 vp minus 1. Sorry, thank you, you're right. A on vp okay, and what do we get there? That's the same as c1a v1 plus cp minus 1 a on vp minus 1, which, because those are all eigenvalues, that's c1 lambda 1, v1 plus cp minus 1 lambda p minus 1 vp minus 1. But a on vp is lambda p on vp, which is lambda p on c1 v1 out to cp minus 1 vp minus 1. So I have that these terms are equal to these terms. So if I move everything to the left-hand side and combine like terms, I get that c1 lambda 1 minus lambda p. Okay. Plus cp minus 1 okay, so I moved everything to one side of the equation, combined all the like terms, but look at all these things. Look, all these coefficients are non-zero, because none of these ones are 0, because all of the eigenvalues are distinct. Okay, and furthermore, you can't have all the C's can't be 0 either. Because that would imply that V sub p is 0, and we already said that V sub p was not, all the V's were non-zero. So what's the contradiction here? Someone can spot me. Why is this then a contradiction?
Because if the equation wants to be valid, then all the lambdas should be the same, which means the set of eigenvalues are not distinct.
Right, yeah. So if the eigenvalues are distinct, how is this a contradiction? What part of the proof did I just contradict?
All eigenvectors corresponding to distinct eigenvalues are
Nice. Wait, was it Rohan? Rahul? Nice, Rahul. Yeah, Rahul got it. Yeah, man. It's this part that that P was the smallest index. Dang it. That P was the smallest index such that this set was dependent. So V1 up to Vp minus 1 are independent. So that's the contradiction. Okay. In math, when you come up with a contradiction, you do two arrows crashing into each other. Okay, cool. So there's your little proof. Okay. Now, I'm not going to have time to do similarity. I think we can do a quick little quiz question. Let's see if you can tell me the eigenvalues for this matrix on Socrative, then you can go. Okay, let me start the quiz. Oh, and I got to see what the eigenvalues are also. Okay, yeah, no answers yet.